sound is on now. Great. Hi, everyone. My name is Justin. I'm really honored to be here today to talk to you a little bit about how we can prove the semantic equivalence of programs using very special kinds of syntactic program transformations with a technique that my collaborators and I call equivalence by canonicalization with applications in synthesis-backed refactoring. Okay, now pattern matching is great because it makes handling cases of an algebraic data type like maybe or result really easy and uniform. Like in this example right here where I'm pattern matching over a maybe data type. But sometimes I'd argue that library combinators can be a little bit easier to read. So in this case, I have a list object and it's great that I can pattern match on it and handle the cases independently. But if I step back and think about the problem a little bit, I might be able to rewrite it to use combinators that looks a little bit more like this, where first we do a filter and then a map and then a concatenation. And this is a phenomenon that I observed while I was running a user study of functional programmers a few years back, where one of them said, I really prefer the pipeline for readability, but it's a little bit harder to write because I don't feel like I have the streamlined version of how it's going to look. Whereas if I write the case down, it's telling me, here's all the possibilities, just handle them. Like start with this one and go to the next one. But maybe you're not a functional programmer. I'd argue that combinators are still useful outside of functional programming. Here's some code that I wrote while I was working with some biologists where we essentially needed to compute a rolling sum over some genomic data. Now, this was a relatively straightforward Python implementation with a nested for loop, and it didn't take me too long to write. But when I went to run it on the entire human genome, it took way too long. So I had to go back to the drawing board and rewrite this program to use NumPy combinators, which is a high-performance computing library for Python. This took me a lot longer, but when I actually did go to run it, it took way, way faster. So the general situation that we have right here is we have this, what we can call direct style code that is maybe a little bit easier to write, but we have this combinator style code, which is more preferable for one reason or another, maybe readability or performance, but it's a little bit harder to write. And the way that I like to think about this combinator style code is it's essentially a backbone of these library components where there's sketch, where the sort of leaves can be filled with more arbitrary expressions. And as I've been describing it thus far, we've been writing this direct style code and then manually translating it into this combinator style code. But wouldn't it be great if we could do it automatically? So that's going to be the main application of this talk. And to sort of set the stage, I'll give you a little bit more of a formal problem statement. The idea is that we're going to be given a reference program in the direct style, P. And what we want to find is a library sketch, S, and a substitution, sigma, subject to the requirement that the semantics of our reference program, P, are going to be equivalent to the semantics of our filled-in sketch, sigma S. OK, now for the purposes of this talk, I'm going to be focusing on one really important subproblem of this general problem, which is, given one of these candidate sketches, how do we actually check the semantic equivalence of it to our reference program? Now, there's a couple of general approaches to this that you might be thinking of. The first one might be something like I/O examples, where we run our reference program, get a suite of I/O examples that we can use as a test suite for our candidate sketch, and see if it passes all of those cases. And this works really, really great in a lot of contexts. But there are some downsides for our particular domain, which is that this is often unsound, and it actually requires running the reference program, which can be a challenge if it's just a snippet in a much larger code base, or if it takes a long time to terminate, or doesn't terminate at all, like in the case of a web server. So maybe the second approach could be something like logical specifications, where we maybe compute some sort of logical summary of our reference program in our candidate sketch and use something like an SMT solver to prove that they're equivalent. And again, this works really great in a lot of contexts, but in our particular domain, this has some downsides. In particular, this will require specifications for all of our library functions. It often requires computing some sort of loop invariance to compute these logical summaries. And sometimes, it's sound in general, but sometimes we have to fall back to bounded verification, and we lose our soundness guarantees. OK, so rather than extending one of these two approaches to work in this particular domain, instead I'd like to ask, is there some way that we can actually bypass the need for input-output examples or logical specifications entirely? So let me give you a little bit of a flavor of what this might look like. Let's say we have this direct style code, which is the sort of pattern matching over the maybe that I had from before. And let's say we have this candidate sketch right here, which uses our library components and has the holes in it. The most naive possible thing that we could possibly do to determine if these two programs are semantically equivalent is to ask, are they syntactically equivalent? Are they the same literal program? And of course, that's going to be sound, but it's not going to work because our candidate sketch is going to be using these library combinators, and our reference program isn't. OK, so we can go a little bit further. Let's say we inline our library combinators. And we can get what I'll call a canonicalized candidate sketch. And now we don't have any of the library combinators, but it's still not syntactically equal to our reference program. So we could maybe do something a little bit more sophisticated, like higher order unification, which is semantic sort of unification modulo the equational theory of the lambda calculus. Unfortunately, there's no series of alpha, beta, and eta conversions that are going to prove that these two programs are semantically equivalent. So we're a little bit out of luck there. But all hope is not lost. If we actually go yet further and we run the classical compiler optimization of deforestation, and then another optimization of partial evaluation, what we actually get is a canonicalized candidate sketch that looks very, very similar to our reference program. It's not quite a perfect syntactic match. In particular, this branch right here, there's a sort of little bit of a difference. But now if we run higher order unification, we actually don't run into any problems whatsoever. We get this substitution right here, which when applied to this candidate sketch in the bottom left, will actually result in a program that is provably semantically equivalent to our reference program in the top left. But hold on, isn't this a little bit weird? We're using these compiler optimizations in a way that they were never intended to be used for. In particular, the traditional use of compiler optimization is for performance reasons. You might get something that looks a little bit like our combinator style program, and then run some sort of syntactic transformation on it, and get something that looks a little bit like our direct style program. In our case, though, we don't really have anything to do with performance in general. Like, sure, maybe the combinators will give us some sort of performance or readability benefit, but our synthesis problem is just concerned with refactoring. So in our situation, here's how we use them. We start with our direct style program, and we start with our combinator style program, and apply the same syntactic transformation to both of them to get a canonicalized direct style program and a canonicalized combinator style program. And then we perform some sort of unification on these resulting programs. This is what we call equivalence by canonicalization. Now, before I dive into the exact technical details of what kinds of syntactic transformations are going to work here, let me zoom out for a moment and show you how this fits into our bigger picture of refactoring, or a synthesis-based framework. And this is what we call component-based refactoring. So the idea is that we start with the user's reference program, and we run a sort of fixed syntactic transformation on it that we call a canonicalization function, and we get a canonicalized reference program. Then we start enumerating candidate sketches and doing the same process until we find a canonicalized candidate sketch that is going to unify with our canonicalized reference program. We can then take the resulting substitution from this unification process, apply it to our candidate sketch, and get our overall solution, which is going to be semantically equivalent to our reference program. And what I'd like to highlight about this approach is that there's no need to encode anything whatsoever in logical systems. You can just use completely off-the-shelf, black box program transformations without worrying about encoding it in a sort of logical system. Now, the benefit of this approach as well is that we can actually leverage decades of research from this community on syntactic program transformations without having to redo anything along those lines, as long as we're sure that the syntactic program transformations satisfy certain properties, because not anything will just do. So that raises the question, exactly what properties do we need in order to satisfy this particular setup that I have right here? That's going to be the first question that we address in this talk. In the realm of compiler optimizations, we might be looking for something like a semantics preserving translation. But in this case, we're actually going to have a little bit of a different answer. The second question that we might be interested in is, when is one of these transformations going to be better than the other? So again, in the compiler optimizations world, we're looking for transformations that might be improving the performance or reducing the memory usage of particular programs. But we're not particularly concerned with that in the refactoring case. And so we're actually going to have a completely different answer than the sort of compiler optimizations world for a second question. OK, so let's dive into this first question. Here's how I like to think about it. We can imagine we have the space of all of our programs, which I've denoted by these orange dots right here. And what we can do is imagine applying our semantic operator to each one of them. Now, in general, we're working with a Turing-complete language, so the semantic operator is uncomputable, and there's going to be infinitely many programs. So we can't actually do this, but let's just imagine it for the sake of this diagram. And let's say that our first program here is going to be our reference program P. OK. Now, what our requirement says is that our reference program needs to have the same semantics as our filled-in sketch sigma s. So maybe we can make our sigma s be the second orange dot right here. Now, the key shift in perspective that allows us to answer this question is not to focus on the semantic operator itself or what these values look like or anything like that, but rather to focus on the kernel of the semantic operator, which I've denoted by these blue ovals here, and which is the equivalence class of programs that gets mapped to the same value. With this shift in perspective, our requirement is that P and sigma s need to be in the same equivalence class that is generated by the kernel. OK, so let's see how canonicalization functions play into this. Let's do the same thing and imagine applying our canonicalization function to all these different orange dots and getting what we have here on the left. We can do the same trick where we look at the equivalence classes that are generated by our kernel. or by our canonicalization function, which I've denoted by these orange rectangles right here. We want to somehow use these orange rectangles to determine whether or not the orange dots are going to be falling in the same oval. So from this sort of intuition in this diagram, what we can require for the answer to our first question is that these syntactic transformations need to be computable, unlike our semantic operator, so we can actually run them. And the kernel of our canonicalization functions need to be a refinement of the kernel of our semantic operators. What this means in terms of the picture is that the orange rectangles cannot overlap two distinct of the blue ovals. And if we have that, then we can do our equivalence by canonicalization check, which is we can say that P and sigma s are semantically equal if phi of P and phi of sigma s are syntactically equal. So the key takeaway that I'd like you to have for this talk, if you remember one thing, would be that we can check the semantic equivalence of programs by checking syntactic equivalence of their images under a canonicalization function. Okay, but our setup is actually a little bit more complicated. In particular, we have these candidate sketch with holes in them. So I'm going to talk about this very briefly, and there's a lot more details in the paper, but at a very high level, we need to generalize our notion of semantics to work for sketches. We need to generalize our notion of kernels to work with more unification-like operators beyond just syntactic equality. And if we set up all the machinery correctly, we get a very similar requirement where the generalized kernel of our canonicalization function needs to be a refinement of the generalized kernel of our semantic operator. Okay, so let's turn now to the second question. When is one of these transformations going to be better than another? And let's say I have this first canonicalization function here, phi1, and another one, phi2, and the only difference between the two is this last arrow here, which I've highlighted in pink. Now, without knowing anything about these canonicalization functions, what they're doing to these programs, or even if they're doing the same thing or similar things to each other at all, I can immediately tell you that phi1 is going to be a better canonicalization function than phi2. And that's because the kernel of phi2 is going to be a refinement of the kernel of phi1. So the same machinery that we were using before to determine whether or not a canonicalization function was sound is actually something that we can use to compare different canonicalization functions to one another. So in terms of the diagram, subject to the constraint that these orange rectangles are going to be contained within a single blue oval, what we want is the largest possible orange rectangles, or the coarsest possible kernel. In other words, a good canonicalization function is one that's going to map many input programs to the same output programs, subject to that soundness requirement that we had from before. Okay, so that's a little bit of the theory of equivalence by canonicalization. How does it work in practice? We implemented this component-based refactoring framework in a tool that we call Cobbler and ran it on thousands of real-world programs. The particular data that I'm going to be sharing with you today is whether or not Cobbler actually improved the programs that we ran it on. Improve is a little bit of a fuzzy notion, and so we need to operationalize it differently depending on the domain that we're talking about. And we implemented both that functional programming example before and our Python to NumPy translation, and we operationalized improving differently for both of those. So for the functional programming case, what we wanted to see is whether or not Cobbler actually subjectively improves these programs to real-world functional programmers. So we ran a user study. What we did is we took the direct style program that we had gotten from the internet and showed that to our functional programmers. And we also showed the machine-translated, automatically refactored combinator style to the functional programmers side by side. We didn't label them in any way or whatsoever. We just asked which one they preferred. For our non-recursive data types, maybe in result, the functional programmers preferred the output of Cobbler in about a quarter of the cases. And for our recursive data type list, they preferred it in about half the cases. And I'd just like to contextualize these results by saying, we took this direct style code that a human had committed to GitHub in a direct style and ran Cobbler on it, and without any sort of manual post-intervention or anything like that, showed it to our functional programmers, and they preferred it in these percentage of the cases. Okay, so for the Python case, what we were interested in is whether the output program was faster, because that's the point of NumPy. We were not just interested in whether it was faster, but whether it was faster even accounting for the synthesis time of Cobbler, because otherwise, what's the point? So we did this by looking at increasing data sizes, which I have on the x-axis here, and measuring the speed up relative to the input program, which I have on the y-axis. And for very, very small input sizes, it's faster to just run the vanilla Python program. But by a data size of 10 to the 6, it's usually faster to take your vanilla Python program, run it through Cobbler, get your NumPy program, run that program, and get your result than it is to just run the original program. Finally, by a data size of around 10 to the 8, the speed up is around 2x. Okay, so to wrap up, there's a lot more in the paper, including a lot about the pragmatics and more about our evaluation. I'm just going to draw your attention to two of them here, which is that we give really concrete tips on how to define a canonicalization function. So if you're interested in applying this to a domain that you care about, I would definitely recommend reading that section. And we also have a performance evaluation of Cobbler, and the TLDR is that the median synthesis time is around half a second. Lastly, we put a lot of work into making our code reusable so that other folks can build on it. So if you're interested in using equivalence by canonicalization or component-based refactoring for maybe refactoring code to use library functions, or theorems to use, or proofs to use lemmas, or anything along those lines, then I'm more than happy to chat about how we can build off of Cobbler. With that, that is equivalence by canonicalization for synthesis-backed refactoring. Here's my homepage, social media, a link to the repo, a QR code for the repo. And the key takeaway that I want you all to have is that we can check the semantic equivalence of programs by checking the syntactic equivalence of their images under canonicalization functions. And this is the image that makes it stick into my head. So with that, I'd like to give special thanks to the functional programming community for participating in my user study and also for sharing it really broadly, which was super helpful. And I'd like to thank you all for listening, and I'm more than happy to take any questions if there's time.
Thank you, Justin. All right, we have time for a couple of questions. Go ahead.
Hi, awesome talk.
Thanks.
I actually think your evaluation at the end was a little unfair to yourself because, you know, most people are going to synthesize once and then run the program a bunch of times. So do you know what the speedups were like if you didn't count for synthesis time?
I think that they're going to be similar to our large data sizes because in that case, the computation of the code is going to be dominating the performance. So I don't remember exactly, but I would hypothesize that it looks around that 2x speedup.
Fantastic, thanks.
Hi, thank you for a great talk.
Thanks.
When you come up with a canonicalization function,
Yes.
Do you have a way to automate in any way deciding which one is better than another, or do you just have to think about it really hard?
That is a great question, and the answer is basically you have to think about it really hard right now. So coming up with a canonicalization function, you know, does require like a lot of domain expertise. We don't really expect like an end user to be able to do this, maybe like they would with I/O examples or something. But once you sort of put in the thought up front, yeah, then it's good to go.
Thank you.
Thanks.
Hi, thank you for your talk. I wanted to ask, NumPy itself is implemented in C.
Yes.
But it's used in Python code. So how can you check syntactic equivalence between the C code and the Python code?
Yeah, this is an excellent question. So as part of our canonicalization function, you know, anything can kind of go into like a syntactic program transformation. And so our sort of like inlining step for this is specialized to those particular NumPy functions, where we run a syntactic translation where it's not really inlining because it's C, but rather replacing it with, you know, a Python implementation of it. In the case of our functional programming, they actually are implemented in the same language, and so we can literally inline. So the functional programming is more general than the NumPy one. But yeah, that is an excellent point.
And I assume that in this case, your implementation is also somewhat simplified when you translate it into Python, because I assume the NumPy implementation is very complex.
Exactly, yeah. I think NumPy is like multi-threaded and like lots of stuff going on, so it doesn't capture all of those details. It just captures essentially
the semantics, the equivalent.
Yeah, it doesn't need to be like a logical specification, and you don't need to sort of take this approach where you do the inlining, but for our particular canonicalization function, that's what we did, yeah.
Okay, thank you.
Hello, great talk.
Thanks.
I have a question just regarding, so sort of the framework of this is the idea of synthesis-backed refactoring for the combinator style programming that you showed. But this orders of, or the issue of like higher order unification, I think is just like a general thing that you run into when you're, say, working with existential variables or proof assistance or even dependent type programming in general. So do you see this as being used in like certain proof assistance to aid in unification there? Or is this just really a stopgap for this sort of aid in programming?
Yeah, that's a really great question. I hadn't thought about sort of richer dependent types or anything along those lines in terms of proof assistance, but I guess if you have like two proof terms that you're trying to, you know, prove are equal, and you off-the-shelf sort of like unification isn't going to work, then I imagine if you sort of set it up properly, you might be able to get a canonicalization function and then do some sort of like unification. It doesn't have to be specifically higher order unification, but it might help it sort of like bridge that kind of final mile. Yeah, I'll think about it. I'm not sure.
Yeah, I guess the second part of this question is also like, would you be able to design sort of a canonicalization function that is somehow able to take independent types? So in the if you have a branch, like sort of the one that you showed before, that happened to carry dependent information per branch for your rewrite or your syntax or something.
Yeah, there's really no restriction on what these syntactic program transformations are. They could be literally anything as long as they satisfy the property. So I think that it could, yeah.
Gotcha. Thank you.
Thanks.
Let's have the next speaker set up while you're answering the last question.
Yeah, this is a great talk. I just was curious if you thought about extending the work to other domains. For example, there's like some work called NGST2 that converted imperative style loops to like, you know, functional style like programs. Have you thought about, do you think your approach could maybe work in that domain as well?
Yeah, I love NGST2 actually. Really cool paper. Would recommend folks to check it out. I think that like where this could fit in is, if I understand correctly, NGST2 uses like a bounded verification check to prove that the final programs are equivalent. You could like slot the sort of neural enumerator into this exact framework right here for our enumerator of like candidate sketches. And I think that they would be like very harmonious. So that's a great question. Thanks.
Awesome. Let's thank Justin once again.
Thanks.